Email that for like
David, you
it's my
can't.
birthday today.
Why did you say hello like that?
Why not?
Okay. Good morning, everyone. Any questions? All right, so what we're gonna do, I'm gonna do a small example about the homework I assigned for today, which is not a lot of you did it, only 8 of you did. So please finish it tonight. And then we keep working along the same line. So I will use the example as a review for what we did. So I pick one of the problems I've assigned and I'll do it. I pick number 19. And let's see what is it about. Okay. So the problem is the following. Okay. We have the graph, the following graph, the graph of the function y equal e minus x. So this is y equal e minus x. And the line ln of 4, x equal ln of 4, and the positive x-axis and the positive y-axis. That's my regional. And we are going to rotate this region, revolve it around the x-axis. That's what we are doing right now. So if we rotate it, we get this kind of, we get those following picture. Something like that. And the problem is we need to find the volume. So when we rotate it, we have a 3D object. The question is to find the volume of this object we got. Okay, so that's really what we were doing last time. So very quickly, I remind you how we proceeded. The way we proceeded was the following. That's the region I want to rotate, ln of 4, y equal e minus x. And we filled up, to find the volume of the solid, what we did was we filled up the solid with little disk. That's really our idea. We filled up the solid with little disk. We found the volume of each disk, and then we add up all the volume. And this gave us the Riemann sum. But where those disks came from? So the way we got those disks to fill up those volume, we did the following. This is the interval, 0 ln of 4. We divided it into pieces, etc. So this is so we divide it into small rectangle. We use those to divide into small rectangle. So this is my rectangle. We call this little xi. And we rotated each rectangle. So we took every rectangle and we rotated. So I'm trying to remind you quickly what we did. So we rotate each rectangle. And that's the typical rectangle. And we rotate it, we get a disk. That's the disk we got. And the idea is if we take every rectangle here and we rotate, we get disk, another disk, and we add the volume of this disk. Right? So what we're going to concentrate on is a typical disk, find its volume, and then add up the volume of all of them. So that's my typical disk. So let's see, radius of a typical disk. So to find the volume of a disk, we need its radius and we need the height. Once I have those two, we find everything. All right. If this is xi, the radius is from here to here. Now, when I'm going to do those problems, and we will do a lot of problems today, I will draw two pictures. One, I don't rotate, so I can label and label clearly. And when I rotate, just to tell you what we're going to get when we rotate a piece. So the radius is going to be basically from here to here. That's my radius. So my radius is this xi, the radius is from here to here. is nothing more than the value of the function at this particular xi. That's this horizontal distance from here to here. So the radius is the value of the function at xi. The height, when I'm going to rotate, this is the height. It's very, very, very thin. So the height here is the delta x. So it's a very, very thin disk, like a quarter almost. The height is delta x. Okay. So the volume of a typical disk is going to be pi times the radius square times the little height. And that's my radius. Okay. Now, the volume of the whole solid is almost equal to the sum of the solid of the disk. So it's nothing more than the sum. That's the second step. So the volume of the whole solid is obtained by adding the sum of the volume of obtained by rotating every rectangle. It means the sum of those. That's what the volume is. Then minus 1. And now the idea is that the larger the n, it means the more subdivision, the more we're going to fill up the solid. So the actual volume is going to be what happened to the sum when n large. When n large, the sum look exactly, by the definition of definite integral, the sum is the following definite integral. E to minus x squared dx. And the limit is which interval I had to divide to be able to cover this region with the rectangle. It's going to be from 0 to ln. All right, so now we have to integrate. Integral from 0 to ln of 4 of pi times e to the minus x squared. It's what? Now I have to start asking you, how can I integrate this? Okay. How can I integrate this? Looks messy. How can I make it not messy? U equal minus 2x. Yes, because e to the minus x squared is nothing more than e to the minus 2x dx. Okay. Now I do substitution. Okay. I put u equal minus 2x. The du is minus 2 dx. I'm going to change the limit because I'm making substitution and I want to change the limit. I will have the upper limit is minus 2 ln of 4, and the lower limit, it means if x is 0, the lower limit will be 0. So finally, I will have the following. Integral from 0 to minus 2 ln of 4 of pi is a constant. I take it out. E to the minus 2x is e to the u. And the dx is a half minus a half d. So we finalize. The final is going to give me minus pi over 2 times e to the u evaluated between 0 and minus 2 ln of 4. So finally, I will have minus pi over 2 e to the minus 2 ln of 4 minus e to the 0. That's v equal to minus pi over 2 times e to the minus 2 ln of 4 is 1 over e to the 2 ln of 4, because I have a minus e to the 0 is 1. Finally, I will have. Now, e to the ln of 4, you know, we can use a calculator, but we really don't need it. It's e to the ln of 4 squared. It means 4 squared. So I'm using the fact that you guys have seen n ln of a is ln of a to the n. So the 2, I can raise it up here. So finally, I will have 1 over 16 minus 1 equal, you finish the problem. Okay. All right, any questions? And I did this problem to remind you what we did last time and to get you ready for your homework. Redo the homework for those who didn't and do the new homework. All right. Part 2, I will do the same problem, very similar. But this time, instead of rotating around the x-axis, we're going to take a problem and rotate it around the y-axis. So very similar idea, but I'm going to change the axis of rotation. So let me set up the problem. The problem is the following. Find the volume. Find the volume of the region, of the solid, obtained by the following. Okay, obtained by revolving the region in the first quadrant. Okay, find the volume of the solid obtained by revolving the region in the first quadrant, which is bounded by. Okay, by the graph of y equal a half x plus 1, the lines x equal to 0, y equal to 4 around the y-axis. Okay, I read the problem again, and then we draw the picture and we do it together. And I want you to help me in this setting. All right, so find the volume of the solid obtained by revolving the region in the first quadrant, which is bounded by the graph of y equal a half x plus 1, which is a straight line, the lines x equal to 0, and the line y equal to 4, around the y-axis. So now the rotation is going to be around the y-axis. So I will draw the picture and we proceed. The big picture and then the little ones. Y equal a half x plus 1, that's a straight line. If x is 0, I am at 1. And then it goes up like that. That's a straight line. And in the first quadrant, so I don't have to worry about the other piece, the line x equal to 0, that's the y-axis. The line y equal to 4. That's the line y equal to 4. And I'm going to rotate it around the y-axis this time instead of the x-axis. And this is going to be like this, rotate. So we're going to have like a vase, this kind of picture. And the question is, we need to find the volume of this picture, which is like a cone. Instead of we did the cone like this. Now we're doing a cone, but a vertical cone. And then the question is, what's the volume? We're going to use the exact same principle, However, instead of taking vertical slices, because we're rotating, when we rotate around the x-axis, I'm going to cover the region with horizontal slices. And I'm going to rotate each one of them. When I rotate each one of them, I'm going to get a disk. So I'm going to cover the inside with a bunch of disk, find their volume, and then add the volume of the disk. That's going to be the stretch. So the same thing, but instead of taking those vertical rectangle and rotate each one of them, I'm going to fill up this region, the solid, with disk, but there are those horizontal disks instead of being vertical. That's the strategy. Okay, questions? All right, and now I want you to be careful because I will draw the picture again. That's the strategy. We're going to draw the picture. So that's really my idea. This is my region. This is my 0. And this is 4. Okay, and this is the line y equal a half x plus 1. as I said, this time I have to take horizontal rectangle and rotate them. To do that, I need to divide the interval on the y-axis into pieces. So I'm going to take a typical piece. Okay, that's my typical piece. And this one I'm going to rotate. So I will rotate my typical piece. This is my typical piece. Sorry, it's right here. And when I'm going to rotate it, I'm going to get also a disk, exactly like I did before. I will get exactly a disk. And now a lot of questions. And this is my typical one. So this is my YR. Now I'm going to ask you a question, and please listen carefully. This is where the mistake showed up on your quiz related to that. Question number 1, what is the height of the disk? Question number 1, and I'm going to pick a student. Arbitrarily, since I really don't know you. All right, Alan asked, that's fine. It's the delta y. Because I'm dividing along the y-axis, my height is the delta y. In this problem, be careful. When I divide along the y-axis, y is my variable. That's not x anymore. Question number 2, what is the radius of the disk? Typical disk. The radius is from here to here. The radius is from here to here. The radius is, I do it in red, that's the radius. That's the yi, and that's the radius. So what's going to be the radius in this problem? The radius is the x distance. So in this problem, I have the y. The y is from here to here. To find the radius, I need the distance, the horizontal distance from the y-axis to the ground. So I know the y, the radius is the x that corresponds to y. So this time, to be able to find the radius, be very careful. I need to solve for x in terms of y. I don't, some of you in the quiz, we had something fairly similar. What they did is that they put x here, they put y here. That's not really the case. You solve for x in terms of y. Listen very carefully because it's new and we do mistakes at the beginning. We have to solve. So we're going to solve for x. Solve for x. So if we do the math, y equal a half x plus 1. If I multiply by y minus 1 equal a half x, x is 2 times y minus 1, because that's the radius, it's the x distance. So it's 2y minus 2. So it's be very careful. So the radius is going to be, the radius of the quiz, I will write it here, is going to be 2yi minus 2. All right, everything in terms of y. So when we divide the interval on the y-axis, everything has to be in terms of y. We don't mix and match. We don't have x's and y within the same piece. Everything is in terms of y. It's the y that I know this time, and I need the x that correspond to this one. Now we are absolutely basically done as far as I am concerned. Volume of a typical disk is pi times the radius square from here to here times the height, which is the delta y. Now, volume of the solid is approximated. Volume of the solid is basically the sum of the volume of those little disks that we are using to fill up my picture. Another idea is that we recognize in this Riemann sum. So when n becomes very large, the definition of the definite integral tells me that the volume is equal to the integral pi 2y minus 2 dy My variable is y, there is no axis, and my y vary from where to where very quickly. Y vary from where to where. It means which interval I need to divide into pieces to be able to cover the whole region with rectangle. Ben, okay, Sami, tell me from 0 to 4. Everything is on the y-axis, everything in terms of y.
Isn't it from 1 since it's +1?
Oh boy, did I draw it wrong?
Yeah, it would.
Oh yeah, thank you very much. Thank you very much. My original picture was from how long? Thanks a lot. All right, very good. It's from 1 to 2. Okay, now how do I integrate this quickly? Now you stuck with this problem. How do you think I can integrate? Pi is a constant. I'm going to take it out. Any idea? We can do substitution. U equal to y minus 2, or how else? The one-way substitution. Who can come up with another idea? Ben, can you think about an idea? Okay, another way to do it is by distributing. Right, just by distributing. And I'll be very, very careful. Be very careful. The mistakes on chat, it's very, very, very careful. What's 2y minus 2 squared? It's not 4y squared minus 4. Absolutely not. Be very careful. So what's 2y minus 2 squared? It's just 2y minus 2 times 2y minus 2. So if you distribute, you're going to get 4y squared plus 4 minus 8y dy. Be very, very careful, because what's 2y minus 2? Okay, if you remember, so it's 2y minus 2. You multiply it by 2y minus 2. You don't get 2y squared minus 4. You distribute, you get 4y squared minus 4y minus 4y plus 4. All right, so you get 4y squared plus 4 minus 8y. So be very, very careful. Typical mistake, very careful. So finally, I get equal to. Pi is a constant. We take it out. Now we have to integrate every term. 4y squared, it means 4/3 y cubed plus 4y. Antiderivative of 8y is 8 times a half y squared, which is going to give me that. Evaluated between 1 and 4 equal at this stage, I think you should be able to fetch. Okay. Please ask questions, and because it's not very easy, it's a different way of thinking. There will be no formulas. We have to come up with our formulas all the time. That's one of the things in this section. You guys will not be given any formula. We have to come up with everything ourselves. Questions? Okay. Right, now we are going to take the following problem. First, I want you to listen a little bit, help me out, and then I will set up the problem. So what we are going to do is we're going to also working with volume, but we're going to rotate a region which is between two curves and see how we can find the volume. So before we start to writing, let me just introduce the idea. So suppose now I'm going to go back, rotate around the x-axis, and then I will rotate it around the y-axis. So suppose I have a region that look like this. That's a region. Okay, and this is the region. It's a region between two curves that I want to rotate around the y-axis. So let me rotate it. Drawing is not my strength, but I will do my best to draw. So I'm going to draw it like that. Now this is the curve. It's going to rotate like this, and this is the line. Okay, so we get this picture. That's what we're going to get. Right? And the question, we're going to get a solid, but the solid has, if you want to think about it, there is a cavity in here, a big cavity in here. Okay, so it's not the whole thing, there's a big cavity. And the question is, what is the volume of the solid? All right, so that's what we are going to do. So instead of before, I took a region that really touches this axis, and we had a solid. That's what I did. So there were no cavity in between inside. This time we're going to find the volume with cavity. Now, the principle is the same. I mean, we're going to do the exact same idea, but there will be a little bit of a change that we're going to discover it in a minute. So the idea will be the same. What I'm going to do is, I said, you know, this is really a hard problem. So what we were going to do is, we're going to take the original region. We're going to revolve around the x-axis. So I'm going to fill it with those little rectangle. And instead of really rotating the whole region, I'm going to rotate every one of those. And fill up the region with the rotation, etc. So now here's my question to you. Please listen very carefully. If I take this typical rectangle, okay, and I rotate it around the y-axis, the x-axis, what do you think I will get? So before, in the previous scenario, I rotated a piece like this. It gave me a disk. Now, if I rotate this typical rectangle,
It'll give you a ring.
we got a ring, absolutely. We're going to get a ring. What we're going to get is, you know, this is how, there is nothing here. So what we're going to get is something like that. That's the inside. I'm rotating it, and that's going to be empty here. And then the outside, we're going to get something like that. That's what we're going to get, like your classmate called it. You know, we got like a ring. We're going to get something like that. And there is a hole in here. So you can think about it, but the way you can think about when we rotate it, we're going to get basically a ring. Another way to say a ring, what we are going to get is actually a disk, if you want, with a hole inside. That's what we're going to get. So when I rotate every rectangle, I'm going to get exactly a disk with a big hole. That's what we get after the rotation, because originally my rectangle here, there is nothing here. So when I rotate it, there is this big hole in here. So if we rotate every rectangle, we are going to get a cylinder, if you want, or a disk with a hole. Okay, so we will do the same principle, but rotation now of every typical rectangle is going to be a different shape. A disk with a big hole, instead of calling it a ring in this class, we are going to call it a washer. So a washer is just nothing more than, imagine you have a quarter and you make a big hole in the middle and you remove this hole, then that's what you get is what we're going to call a washer. And now the idea is we're going to fill this with those washers and find the volume of each one of them and add the volume, okay? So we're gonna do it around the x-axis, and then we're gonna do the same thing, but we will do it around the y-axis, where we're gonna take our horizontal instead of vertical. Questions? So now the question is, what's the volume of a washer in general? And then we go back to the initial problem and we find the volume of each washer by itself and we add that. So that's really the strategy that we're going to do. So it's the same ideas as before, we don't change, but we just change the picture somehow. So this is we are, it's still section 6.3 in the book, we're not changing. So a volume, obtained by rotating region between two graphs, if you want. Obtained by rotating a region between two graphs. Usually it's called the washer's method because we get a washer every time we rotate. So the first thing is what's a washer? So let us define a washer and find its volume. So what is a washer? A washer is nothing more than a disk with a hole, a big hole. Okay. Now let's see what's the volume of a washer. Okay. So let's see what a washer is. So we have, this is the height of the washer. And I have a big disk. That's the center of my disk. And I have a little one inside, not a big one, sorry, I have a hole inside. And that's my washer. Okay. So what's going to be the volume of it? And this is the height of it. So what's going to be the volume of it? Anybody just can think of it? Quickly, it's not hard. What do you think? How would you compute the volume of such a thing? What do you think you need to be able to compute the volume?
You need the radius.
Which radius?
Radius of both the inner and the outer.
Right, we need both two radiuses. So we need the radius of the big disk. And we're going to call it R OUT. OUT stands for outer. Okay, and we need the radius of the little one. This, the little disk. We're going to call it RIN. IN stands for inner. So we need the inner radius and the outer radius. And what's going to be the volume? Volume of the washer. Using the picture is volume of the big disk, if you want, minus the volume of the little disk. Minus volume of the little disk. Okay, it's equal to. Now this height here usually is either my delta x or my delta y. So let me call it this time delta x. That's what's going to be the height in my problem. So let me call it delta x for the time being, which is the height. So it's going to be the volume of the big disk is pi times the outer radius square times the delta x, big disk. Volume of the little disk, pi, the inner radius square times the delta x. So I'm really figuring out the formula here. It's equal to, now sometimes this is simplified a little bit because I have pi and delta x as a common factor. The way we write it is like that. We're going to factor out the pi and the delta x. And what we are going to be left with is the outer square minus the inner square. And that's the traditional formula we use for the volume of a washer. It's very easily derived from the picture, nothing deeper than that. Very good. Now I'm going to go back and we're going to solve a problem, take a region between two curves and find its volume. Can I move the paper for those who are taking notes? Yes, no, in between. Could you take radius of the outside? Wait. Okay, let me go back and check. Could you take radius of the outside and subtract this one and put, then compute it into? No, you cannot do that. You cannot do that. That's the formula that you have to use. You cannot take, if I'm understanding your question, you cannot take that square. Is this your question? Yes or no? Absolutely not. Those are not equal. Those are not the same. because this minus that is not, that's the same mistake you did a minute ago. Absolutely not. Okay, it's the outer square minus the inner square. And you factor out those two. Okay, so absolutely that's not correct. All right, so let's take this region. Okay, I read it while you guys are writing. Let R be the region bounded by the graph of y equal 2 root x, y equal x. Find the volume of the solid obtained by rotating R about the x-axis. So I read the problem while I'm graphing at the same time. So first I do the graph and then we go slow. So R is the following region. It's bounded by y equal 2 root x. That's the graph of root x. Y equal to x. Y equal to x is a straight line. So they're going to meet somewhere. We're going to find. So this is my region. So y equal to root x. Y equal to x. And we're going to revolve this around the x-axis. So that's a region in between. So that's really basically like the problem we did. And that's going to be rotated. Okay. We're going to get this kind of picture. And the question is, what is the volume of this solid? So it's, as I said before, you imagine it's a big solid that you're taking away a big chunk from it. And that's the cavity. That's really the cavity. And we're going to find the volume. Though we will do it by exactly the same approach. We're going to split this into pieces. And first we have also to find what this is going to be. We're going to split into pieces, and instead of rotating into a little rectangle, and we're going to rotate each one of them. And each time we rotate one, you will get this big washer that we need to find its volume. So let's get to. So I will start on a new picture. So I'm going to do that now. My curve and my other curve. And we're revolving around the x-axis. So step number one, I need to find the intersection point because I need to know which interval I need to split into pieces to divide. So let's find the intersection point. Intersection point. Okay, to find the intersection point, I have to set 2 root equal to x equal x. And then solve for x. Some of you, I gave a similar problem on the quiz, and some of you had some difficulties with that. So the way to do it is, because I have the square root, I need to square both sides so I can get rid of the square root. So if I square both sides, this, square it, it means I multiply it by itself, it's going to give me 4x equal square x squared. Now I need rewrite it in the form x squared minus 4x equal to 0 to be able to solve. I factor out my x. So be very careful. A lot of you didn't, they picked up the answer from the calculator, but you couldn't really do it algebraically, but we should. X equals 0 and x equal to 4. And now once this x equal to 0 and this is 4. And to make sure I'm having the right answer, I plug 4 here, x, and I plug it here, and I see those two, the y's are the same. If I plug here, y equal to 4. If I plug 4 here, square root of 4 is 2, 2 times 2, so I am doing correctly. Okay, so I know I got the right point. So this is my 4. So I took care of that piece. Okay. Now, the division start, and I focus only on one piece. This is my xi, and this is the piece. This is my rectangle, and from here to here, this is my delta x. So now everything with respect to x. Now I will rotate this piece. So I'm going to rotate it here for the clarity. I leave this graph for labeling, and I do this just a little bit. So this is my little picture. And this is the one I'm going to rotate. Okay. So now I'm going to rotate it. I'm going to get something like that. That's my washer. That's my washer, okay? Now, question addressed to you. So this is the piece, this is my XI. So again, one more time, that's the rotation. We're gonna get something like that. Now question, what's gonna be the inner radius? And what's gonna be the outer radius? So I need to find the volume of the washer. Two things are important, absolutely. I need the inner radius, I need the outer radius, and I need the height for the typical washer. Once I find all those, the rest is easy. All right, what's the inner? Now I stop, and I want answers from everyone. Ryan Kowalski. What do you think the inner is going to be? Look at the picture very carefully. Are you with me, Ryan?
Yeah, I'm here.
Okay, give it your best shot. Right, wrong, I don't care. Give it your best shot.
Oh my gosh. I actually have no idea.
Okay, in this picture, the inner radius is from where to where? From the x-axis, right?
Yeah.
To here. Am I right?
Yes.
Are you sure?
Yes.
Don't be, yeah, okay. So on this graph, it's from the x-axis to this curve here. This is my xi. It's from here to here. That's the inner. Any sense? Am I right?
Yeah.
So what's the inner? If this is xi, what's the value from here to here in terms of xi? Remember, this point is on this graph. So it's equal to what? Let me take you back here. This is my line, y equal to x. Okay? If I tell you this is 2, how much from here to here? Don't be afraid. This is the line y equal x. If I tell you this is 2, what's going to be this vertical distance? Okay, I don't like
2.
it. Absolutely, don't be afraid. It's 2.
Yeah.
Don't be
Yeah,
afraid.
it is 2.
It is 2, don't be afraid. If I tell you this is 3, how much? If this is 3, don't be afraid.
1.
No, why 1? We are still on the line y equal to x. If this is 3, this is the graph of y equal to x. It means if this is 3, this has to be 3 as well, because it's on the graph of this function. So what I'm trying to say, if this is xi, the inner is going to be also xi, because this is the graph of the function y equal to x. It means every point on this graph, whatever the x coordinate is, the y coordinate is going to be the same. This is my xi. Also, am I making any sense?
Yeah, it makes sense.
Little bit. So my inner is xi. What is my outer? What is my outer on the picture? My outer is, this is the center of rotation because I'm rotating around the y-axis. My outer is from the axis of rotation till the outer curve, because that's my outer radius from here to here. So it's from the axis of rotation to my outer curve. This is my outer. Okay, my outer is equal to what to what? equal to 1. This is xi. My outer is here, from here to here. It's equal to what? Anybody? This is the curve y equal to root x. What does this mean? It means if I know xi, this point here is whatever the value of x is, it's 2 times. That's what this means. So if this is xi, my outer radius is the distance from the axis of rotation to basically the top curve. It's going to be 2 times the square root of xi. My height is a little bit of this. It's my delta x. Okay, so my inner radius is from the axis of rotation till the curve, which is the closest to the axis of rotation. It means the bottom curve. So this is the horizontal distance from here, the vertical distance, sorry, from the axis of rotation to the inside curve, which is xi. And the distance from the axis of rotation to the outside curve is 2 times the square root of xi. It means the value of the function at xi. And now, believe me, I am almost done. Volume of a typical washer. So the heart of the whole problem is to find those. Once we find them, we're done. Volume of a typical washer is pi times. That's the height. The outer radius square minus the inner radius square. So that's the outer radius, which is the distance from the axis of rotation to the outer curve. That's the outer radius. And this here, the inner radius. And now the total volume, the volume of the solid, is going to be pi times, sorry, not pi. It's going to be the integral. That means the sum of those volume, 2 root x square minus x square. And the integral has to go from 0 to 4. So finally, this is equal to pi is a constant, get it out, integral from 0 to 4. 2 square root of x squared, it means 2 root x times 2 root x. This gives me 4x minus x squared, the whole thing dx. Now finally, I integrate. Pi is a constant. Antiderivative for x is 4 times a half x squared. Antiderivative of x squared is a third x cubed. The whole thing between 0 and 4. Okay. I will start another problem because, as I said, this is not very easy, but it's not very hard also. So we will do a lot of problems. So I will do one now, and then I will give you the homework. You struggle with it, and we fix it tomorrow. So I will do that as fast as I can. Find the volume of the solid obtained by rotating the region in the first quadrant bounded by the graph of y equal 4x cubed, y equal 4x about the x-axis. So verbatim the same, I'm just changing the function that we are going to rotate. So as usual, I will first see what am I doing, what's my picture. Y equal 4x cubed is a graph that looks like this. That's the x cubed. Y equal 4x, it's a line like that. And the intersection, if we set 4x cubed equal to 4x, not for the intersection. It means 4x cubed minus 4x equal to 0. I can factor out the 4x, get x squared minus 1 equal to 0. I get x equal to 0, my first intersection point, which I knew that, and I get x equal 1 from here. And to make sure, if I plug in 1, I get a 4. I plug in 1, I get a 4, and this is 1. So that's really the region, and that's my axis of rotation. Okay. And I need to find the volume. So I said, okay, let me concentrate only on one little piece, and then I add the volume. So I take this little piece right there, and I rotate it. And let me make sure what we, and this piece, this is here, right here, this is my xi. So, and this is my 4, and I'm gonna divide this interval and rotate each one. This here is xi. So while I'm rotating, I'm gonna rotate this piece, we're gonna rotate that. So I will rotate, I will get this washer up here. And that's the whole. That's the whole of the washer. So wouldn't be 1 instead of 4 for the intersection point, Alan? Oh boy, I'm doing stupid mistake.
Yeah, that's
Oh,
what I'm
you're
saying.
absolutely correct. Thank you very much. All right, so now I'm gonna concentrate on the washer, and I'm going to find the inner radius, the outer, and the height. Okay, all right, and let me remind you, this is y equal 4x, and this is y equal 4x cubed. Very good. Now, to finish quickly, what is the inner radius? And let me pick somebody. I don't know. I mean, I really don't know you. Madeline, are you with me?
Yeah. Did
Okay.
you ask what the
inner.
inner?
Yeah. First in the picture. It's
The
from the,
inner is 4x cubed.
is she right? Yes, no. Is she
Wouldn't
correct?
it just be 4xi cubed?
Yeah, absolutely. But the function is correct. It's from the axis of rotation to the bottom curve. That's my inner. She's absolutely correct for xi cubed, because this is xi. Okay, now Julian, what's the outer? Julian, are you with me? Okay, that's all right.
Is it 4xi?
It's for xi, absolutely. It's from the outer, from the axis of rotation. That's what we are rotating around. That's what we are rotating around to the outer curve. So the outer is 4xi. What's the height? Because I know that I'm 3 minutes over. What's the height? Julian, quickly. I'm rotating this disk. My height is my delta x. All right, my height is my delta x. So now the total volume is going to be, I'm skipping one step, integral from 0 to 1 of pi times outer square minus the inner square times the height. That's how I read. And the rest is you do the math. Okay, sorry for taking 4 minutes longer. Okay, so please do the homework. You're gonna struggle with it, I'm telling you, because I'm giving you a problem where the rotation around the y-axis. You're gonna struggle with that, but that's not a big deal. Tomorrow we will take care of that. Okay, I have office hours right now at 9. Please show up. I did tell some of you to show up to help you with your quiz. And if anybody has any question, please stay.